Right, so today we are going to discuss about the VSEPR theory. And for those of you who haven't understood VSEPR theory till now, after this video, I'm sure you might be wondering that why you could not understand VSEPR theory, because it is such a simple topic, and I'll make it even more simpler for you to understand how to predict structures with the help of the VSEPR theory, right? So I won't go into the full form and all that things because you already know the theoretical part of VSEPR theory. I will just focus more on how to apply the VSEPR theory uh, pertaining to your entrance exams, or if in your academic exams also you are given some compound and they ask you the structure, the shape or the geometry of that particular molecule, then you can easily predict with the help of VSEPR theory, right? So I'll take each and every example and explain that how we utilize the VSEPR theory. Okay. Now, first of all, you have it is all about the number of electron pairs. So you have to find the number of electron pairs in the compound. So any given compound you have to first and foremost find the number of electron pairs in the given compound. And how you do that is, see, for example, if you have, let's say, CO2. Let's say you have CO2. This is your compound. Now in CO2, you have to first see how many valence electrons are there with carbon. Whichever the central atom is there in the compound. First of all, you have to identify the central atom. So the central atom in this compound is carbon. Now carbon has 4 electrons in its valence shell. Okay. So carbon has 4 electrons in its valence shell, and all the 4 electrons are participating in bonding because it's forming a double bond with this oxygen and it's forming a double bond with this oxygen. Okay. So all the 4 electrons are participating in bonding. Now what I mean by electron pair is the number of bonding pairs, that is represented by Bp, and number of lone pairs, that is represented by Lp. So to find out the structure or the geometry of the compound, you have to find the number of bond pairs plus the number of lone pairs for any compound. You have to identify how many bond pairs are there and how many lone pairs are there. Now it does not matter whether it's a double bond or a single bond. A lot of students get confused here, so please listen to me carefully. It does not matter whether it's a carbon singly bonded to an oxygen or a carbon doubly bonded to an oxygen. You always take bond pairs equal to 1. There will be one bond pair between C double bond O or C single bond O. It does not matter how many, if it's a multiple bond or it's a single bond, the bond pairs will remain 1. So if there is a bond between carbon and oxygen, irrespective of whether it's a multiple bond or a single bond, you will take one bond pair. So to this carbon we have 2 bond pairs attached. So we have 2 bond pairs. Okay. And how many lone pairs? Since all the 4 electrons are participating in bonding, there's no lone pair on the carbon. Okay. It might look confusing right now, but just follow my video for a little while and things will clear out on its own. So there are 2 bond pairs. Now for 2 bond pairs, the VSEPR theory predicts that the geometry is linear. So this compound has linear geometry. Alright. So according to VSEPR theory, I'll just write it down. If we have 2 bond pairs, then the structure is linear. Okay. If we have 3 bond pairs, then the structure is called, the geometry is trigonal planar. Okay. So the difference between the shape and the geometry. Right now I'm talking about the geometry. 3 bond pairs, it's trigonal planar. 4 bond pairs, it's tetrahedral. Okay. Then for 5 bond pairs, it is trigonal bipyramidal. Trigonal bipyramidal. Okay. For 5 bond pairs. For 6 bond pairs, it's octahedral, and so on and so forth. For 7, it is pentagonal bipyramidal, and it goes on like that. So these 6 are the most important. Alright. And then this is the geometry. So this is the basic geometry for these compounds which have 6 bond pairs. See, I've misrepresented it. It should not be bond pairs. That's what most of the books show, that 6 bond pairs. It's not actually bond pairs, it's electron pairs. Okay. And electron pairs comprises of bond pairs and lone pairs of electron both. So I've written over here bond pairs. This is actually incorrect. It should be 3 electron pairs or 5 electron pairs, like that. Okay. So these, just correct this, that instead of bond pairs it should be electron pairs. So what I mean by that is, for example, if a compound has 4 electron pairs, so the geometry is tetrahedral. But this 4 electron pairs can also be because of, let's say, 3 bond pairs and 1 lone pair. A compound could have 3 bond pairs and 1 lone pair. Then also it will fall into this category. Or a compound could have 2 bond pairs and 2 lone pairs. Then also it will have 4 electron pairs. So then also it will fall in this category. Similarly, if we talk about 6 electron pairs, how can these 6 electron pairs be fulfilled? Either a compound could have 6 bond pairs and no lone pairs, or a compound could have 5 bond pairs and 1 lone pair, or 4 bond pairs and 2 lone pairs. So like this, there are many permutations and combinations by which a compound can accommodate these 6 electron pairs. So for all those compounds which have a total of 6 electron pairs, the geometry will be octahedral. The shape will depend on the number of bond pairs and lone pairs, right? Okay, so we took example of CO2, and CO2 is linear. Okay, now let's take another example of a compound, let's say BF3. Now boron in its valence shell has 3 electrons. Okay, and all the 3 electrons are participating in bonding because there are 3 fluorines, so it is participating with 3 fluorine atoms. I mean, in bonding it is participating with 3 fluorine atoms. So we have B, if I show you the structure like this. So 3 electrons it has in its valence shell, all the 3 are participating in bonding with fluorine. So it has 3 bond pairs but 0 lone pairs, because now there is no electron left which is not participating. Lone pair means non-bonding electrons, or the ones which are not participating. So it has 3 bond pairs, and like I told you, according to the VSEPR theory, the geometry as well as the shape for 3 bond pair compound is trigonal planar. So this compound has BF3 has trigonal planar structure, right? But what if we talk about a compound which has 2 bond pairs and 1 lone pair? If I take a compound SnCl2, now Sn is in the group of carbon, so that means it has 4 electrons in its valence shell. Now 2 of the electrons are participating in bonding, like right, chlorine gives 1 electron, Sn gives 1 electron. Similarly, Sn gives 1 electron, chlorine gives 1 electron over here. So the stannous or the tin is giving 2 electrons. So that means it has 2 electrons which are not participating in bonding. So these are the lone pair of electrons. So this structure is basically 2 bond pairs plus 1 lone pair, because they are pair of electrons. There is a pair of electrons that is not participating. So 1 lone pair and 2 bond pairs it is forming. So the number of bonds that a compound has, it is equal to the bond pairs. Now this also in total has 3 electron pairs. Okay, this in total has 3 electron pairs. So that means the geometry, the molecular geometry of this compound is trigonal planar. The molecular geometry of this compound is trigonal planar. But if you talk about the shape is bent, or it is sometimes also referred to as V-shaped. So it is bent or V-shaped, and the angle between this angle is less than 120 degree. Sorry, this angle is less than 120 degree. This angle over here, it is less than 120 degree, and it's called bent or V-shaped. So you can easily Google it, VSEPR theory shapes. If you Google VSEPR theory, VSEPR, VSEPR theory shapes, you will get a table describing all the bond pairs and lone pairs and what is the shape. Like for 3 bond pairs and 1 lone pair, what is the shape? For 4 bond pairs, 2 lone pairs, what is the shape? So you will find all the shapes. I'll take each and every example, but in Google, if you go on to the images, it is very easily perceivable that how they have defined. I mean, they have made a table, and you can easily look into the table and remember the shapes, right? So you have to memorize the shapes. There is no other alternative. Okay. So 2 bond pairs, 1 lone pair, it's bent or V-shaped, but the molecular geometry will be trigonal planar. Why? Because it has 3 electron pairs. So the molecular geometry is dependent on the electron pairs, and the shape depends on how many bond pairs and lone pairs are present. So for BF3, the molecular geometry is also trigonal planar, and the shape is also trigonal planar. So both are trigonal planar for BF3, right? Now what about methane, CH4? Now CH4, it has 4 bond pairs. I mean, you know the tetrahedral geometry, I will not draw it. CH4. So it has, just let me check for the video once. Yeah, so CH4, it has 4 bond pairs, right? Because each of the carbon is the carbon is forming 4 bonds with hydrogen, right, in methane. So it has 4 bond pairs and no lone pair, because carbon has 4 valence electrons. All four are participating in bonding. So it has 4 bond pairs. And what did I tell you? 4 bond pairs. That means the structure is tetrahedral. Since it has no lone pairs, so the molecular geometry is also tetrahedral and the shape is also tetrahedral, right? So if a compound does not have any lone pairs, so in that case, whatever is the molecular geometry, that is the shape of the compound. So for example, over here, this has no lone pairs, it has only 4 bond pairs. So that means it has 4 electron pairs. And like for 4 electron pairs, I told you the molecular geometry is tetrahedral. But since it does not have any lone pair as well, so the shape is also tetrahedral. Like in case of BF3, it had 3 bond pairs and 0 lone pairs. So in that particular case also, the molecular geometry and the shape were similar. But as soon as a lone pair is introduced, the shape is distorted and the molecular geometry is different and the shape is different for a compound. Okay. Now let's talk about ammonia. Now in ammonia, we have NH3. Now nitrogen has how many valence electrons? 5 valence electrons. 3 of the electrons are participating in bonding with this hydrogen. So if I draw an NH3, 3 of the electrons are participating in bonding with this hydrogen. But what about the rest of the 2 electrons? It has 5 valence electrons, like I just said. 3 of the electrons are participating in bonding. So that means there's one lone pair that is there, because 3 electrons are participating in bonding, so there's one lone pair. So that means we have 3 bond pairs and 1 lone pair. So we have 3 bond pairs and 1 lone pair. So what does that tell you? That tells you that this compound ammonia is it is referred as trigonal pyramid or pyramidal, whatever you like to call it. Trigonal pyramid. So the geometry, the shape, the molecular geometry is again tetrahedral because it has 4 electron pairs. If you add this 3 bond pairs plus 1 lone pair, you get 4 electron pairs. So the molecular geometry is tetrahedral, but the shape is trigonal pyramidal. So for a compound which has 3 bond pairs and 1 lone pair, the shape is trigonal pyramidal. One more example of this compound is XeO3, xenon compound, XeO3. Now if I draw the structure for XeO3, let me just draw you the structure for XeO3. So we have double bond oxygen, double bond oxygen, double bond oxygen, and a lone pair on xenon. Why? Because xenon is doubly bonded to 3 oxygens, so 6 electrons are participating in bonding. Okay, there are 6 electrons participating in bonding, but I told you that whether it is a multiple bond or a single bond, it does not matter. You have to take only 1 bond pair per bond. So XeO bond, even though it's a double bond, you will take only 1 bond pair. So there are 3 bond pairs. So we have 3 bond pairs. Okay, and so since it's a double bond, so 2 electrons are being contributed by the xenon for each oxygen. So we have 2 electrons over here, 2 electrons over here, 4 plus 2 electrons over here, 6. And xenon is a noble gas. It has 8 electrons in its valence shell. So that means it has 6 electrons are participating in bonding and there's 1 lone pair. So 3 bond pair plus 1 lone pair. That means this is also trigonal pyramidal. What does that mean? That NH3 and XeO3 both have the same molecular geometry and the same shape. And you can say one application of this VSEPR theory is to find out the point group. Now for ammonia, all of you know that the point group is C3V. For ammonia, the point group is C3V, right? So if the shape and geometry of XeO3 is similar to ammonia, that means that XeO3 also has C3V point group. So sometimes it becomes very easy if you know the molecular geometry and shape of one particular molecule and you find out that the other molecule also has the same shape and molecular geometry, then the point group is also going to be the same for both the compounds. So from one compound you can deduce the point group of other compound, right? So I am talking about 4 electron pair compounds. So in first of all I talked about, I'll write down over here. First of all we talked about 2 bond pairs, right? Then we talked about 3 bond pairs, right? then we talked about 2 bond pairs and 1 lone pair. After that we talked about 4 bond pairs, right? Then we talked about 3 bond pairs plus 1 lone pair. This is the case of ammonia. I'll just write down NH3. And then now we are going to talk about 2 bond pairs and 2 lone pairs. Okay. So for 2 bond pairs and 2 lone pairs, again there are 4 electron pairs. So the molecular geometry is tetrahedral. But what about the shape? So what is the example of 2 bond pairs and 2 lone pairs? The simplest example is water. So oxygen has 6 electrons in its valence shell. 2 are participating in bonding. So that means it has 2 bond pairs and 2 lone pairs. Okay, as simple as that. So it has 2 bond pairs, 2 lone pairs, and the geometry and the shape is, the molecular geometry is 4 electron pairs. So the molecular geometry is tetrahedral, but the shape is bent or V-shaped. Now if you remember clearly that the shape for 2 bond pair and 1 lone pair was also bent or V-shaped. Like I had discussed the example of SnCl2. SnCl2 also has a bent or V-shaped structure. So it has a shape that is bent or V-shaped, and this compound also has a shape which is bent or V-shaped. But the molecular geometry was trigonal planar for SnCl2. But for water, the molecular geometry is tetrahedral. So that is the difference. The molecular geometry is different. The shape, the name of the shape is same. This is also bent, that is also bent. But the molecular geometry is different. And the bond angle over here is somewhere around 109 degree. So like I discussed, for 2 bond pairs and 1 lone pairs, the bond angle was less than 120. In this case, the bond angle is less than 109 degrees. And the reason for that is this oxygen and this oxygen are, the lone pair on this oxygen, there are 2 lone pairs. So both the lone pairs are repelling each other. Okay. Now since both the lone pairs are repelling each other, this bond is getting closer, and that is why this angle is getting lesser. This angle is less than angle for 2 bond pairs and 1 lone pairs, because see, if you imagine a scissor, okay, if you imagine a scissor like this, right? Now if both of the fingers are repelling each other, so they will repel, and because of this so because of this repulsion, this bond angle will reduce. Okay, it's a little difficult for me to comprehend, to show it to you, but basically this angle gets reduced because of the lone pair repulsions, right? So we discussed about tetrahedral. Now let's talk about trigonal bipyramidal, the molecular geometry that is trigonal bipyramidal, that is 5 electron pairs. So first we'll talk about 5 bond pair compounds which has 5 bond pairs. So the simplest example is PCl5. So in PCl5 we have basically we have 5 bond pairs, because phosphorus has 5 electrons in its valence shell. All 5 are participating in bonding. So PCl5 has a structure trigonal bipyramidal. So it's very, very simple to understand. If you would like me to draw the structure, so it looks something like this. These 2 chlorines are above and below the plane. If you can imagine, one of the chlorines is coming out of the whiteboard, the other one is going inside the whiteboard, and then we have 2 chlorines over here. So this is your trigonal bipyramidal structure. This chlorine is coming above these 3 chlorines are in the plane along with the phosphorus. 1 chlorine is below the plane and 1 chlorine is above the plane, right? So it has 5 bond pairs. If I talk about, so the molecular geometry is also trigonal bipyramidal, and the shape is also trigonal bipyramidal. What about if I talk about 4 bond pairs and 1 lone pair? What is a compound that you can imagine? SF4. SF4. So there are 4 fluorines. So there are 4 bond pairs. So sulfur is forming 4 bonds. So there are 4 bond pairs. But sulfur has how many electrons in its valence shell? It is in the group of oxygen. So it has 6 valence electrons. And 4 are participating in bonding. That means it has 1 lone pair as well. So there is 4 bond pair and 1 lone pair. And the geometry of such compounds is called seesaw geometry. Sorry, not the geometry. I'm sorry. The shape is called seesaw. The molecular geometry is trigonal bipyramidal because there are 5 electron pairs, 4 bond pair plus 1 lone pair, that means 5 electron pairs are there. But the shape is seesaw because we have 1 lone pair, and this 1 lone pair distorts it from the ideal geometry of trigonal bipyramidal, and that is why it has seesaw geometry. Okay, right. If you want to know the structure, seesaw geometry, I'll just draw it. So we have sulfur, we have lone pair of electrons, we have 2 fluorines, then we have 1 fluorine above the plane and 1 below the plane. So basically this lone pair, these 2 fluorines and this sulfur are in the plane. This fluorine is going inside the plane, and this fluorine is coming outside the plane like this. So there's 1 fluorine like this, 1 is inside like that, and then we have 2 fluorines in the plane along with the sulfur and the lone pair. Okay. Now let me just check once again. Yeah. So it's quite a long video. I did not expect that VSEPR theory will become this long, but anyway. So what about let's say now let's talk about we discussed 4 bond pair, 1 lone pair. Now 3 bond pairs and 2 lone pairs. 3 bond pairs and 2 lone pairs. So if we talk about 3 bond pairs and 2 lone pairs, what we can imagine is 3 bond pairs and 2 lone pairs. So if I take an example, ClF3. Here chlorine is the central atom. Chlorine is forming 3 bonds because there are 3 fluorines, so it is forming 3 bond pairs. So we have 3 bond pairs, and how many lone pairs? So chlorine has 7 electrons in its valence shell. 3 are participating in bonding. So that means there are 4 non-bonding electrons or 2 lone pair of electrons. 4 non-bonding electrons, or if you talk about pairs, then 2 lone pair of electrons. There are 4 electrons that are not participating in bonding. So that means it has 2 lone pairs. So we have 3 bond pairs and 2 lone pairs, and the shape for these compounds is T-shaped. Again, the molecular geometry is trigonal bipyramidal because it has 5 electron pairs, 3 bond pair plus 2 lone pairs, so 5 electron pairs. But the geometry is what the shape is T-shaped. Okay. Now, since this video is has become very long, I will not draw the geometry again and again. I mean the structure again and again for such compounds. You can just imagine. You can just see it online. Okay, because it will become very long. So we have discussed 3 bond pairs and 2 lone pairs. Then we have compounds which have 2 bond pairs and 3 lone pairs, such as XeF2. So XeF2 means 2 bond pairs, and xenon has 8 electrons in its valence shell. So 2 of the electrons are participating in bonding. That means there are 6 non-bonding electrons or 3 lone pairs. So it has 2 bond pairs and 3 lone pairs. So the geometry is trigonal bipyramidal. But what about the shape? The shape for such compounds is basically linear. These compounds also have linear shape. So that compound over there, which had 2 bond pairs, was also linear. The shape was linear and the geometry was also linear. Here the molecular geometry is trigonal bipyramidal for XeF2, but the shape is linear. Okay. So any compound with 2 bond pairs and 3 lone pairs will have linear shape, right? Similarly, we can discuss for the case of octahedral compounds with octahedral molecular geometry. In octahedral, if we talk about SF6, it has 6 bond pairs, so the molecular geometry is octahedral and the shape is also octahedral. Sulfur has 6 valence electrons, 6 of the electrons are participating in bonding since there are 6 fluorines. So SF6 has octahedral molecular geometry and shape. What about let's say BrF5? So here the central atom is bromine. It has 5 fluorines, so 5 bond pairs. 5 of the electrons are participating in bonding. Bromine has 7 valence electrons. So there's 1 lone pair. So there's 5 bond pair and 1 lone pair. So if a compound has 5 bond pairs and 1 lone pairs, the total electron pairs is 6. So the molecular geometry is octahedral, but the shape is square pyramidal. And the shape is known as square pyramidal. And what does it look like? So if I draw bromine in the center, we have 5 fluorines. 1, 2, 3, 4 like this. They all are in the same plane. Then we have one fluorine above, and we have a lone pair of electrons below the plane. So this is the structure which is known as square pyramidal BRF5. 5 bond pairs and 1 lone pair. The shape is square pyramidal. The molecular geometry is octahedral. What about 4 bond pairs and 2 lone pairs? If I take a compound with 4 bond pairs and 2 lone pairs, I'll take a similar example, BRF4 minus. So whenever you have a negative charge, I'm glad that I remembered this this negative and positive charge concept. Whenever there is a negative charge on the compound, on the whole compound, you always take this negative charge as 1 electron on the central atom. Whenever you have a charge, like over here it's a negative charge, you will say plus 1 electron on the central atom. If it has a positive charge, then minus 1 electrons. I mean, if there's a negative charge, you add 1 electron to the central atom. If there's a positive charge, you subtract 1 electron from the central atom. Because negative charge means excess of electrons. That means there's 1 electron excess on the central atom. Similarly, if there's a positive charge, that means deficiency. So you can take out 1 electron from the central atom. So it is BRF4 minus. Now definitely there are 4 fluorines, so it is 4 bond pairs, right? But what about lone pair of electrons? Now bromine has, if it is forming 4 of the electrons and 4 of the electrons are participating in bonding, then that means that one of the electrons, I mean there are 7 valence electrons, 4 are participating in bonding. So that means there are 3 valence electrons that are there in bromine. So there are 3 valence electrons. But we have a negative charge as well. And what did I tell you? If you have a negative charge, you add 1 electron to the central atom. So that means there are 4 non-bonding electrons with bromine. So 4 non-bonding electrons means 2 lone pairs. So the compound has 4 bond pairs and 2 lone pairs, and the molecular geometry will remain the same, octahedral, because total 6 electron pairs are there. But the shape is called square planar. So for a compound with 4 bond pairs and 2 lone pairs, the shape is square planar. That means it is a planar compound. So if you draw the shape, we have 4 fluorines and bromine in the plane, and we have lone pair of electrons above and below the plane like that. Okay, and then there's a negative charge which you can show like this, minus, on the whole compound. Okay. Right, so we discussed about 4 bond pairs and 2 lone pairs. Similarly, we have 3 bond pairs, 3 lone pairs. That is also octahedral geometry, 3 bond pairs and 3 lone pairs, but it is called T-shaped again. And then we have 2 bond pairs and 4 lone pairs. Again, the geometry is octahedral and the shape is called linear. So these are some of the other compounds that have this kind of shape. I mean, you can take some examples. I do not want to waste my time. I think I have explained you in as much detail as I could, and I don't think now you might be having any doubts. So just go ahead and solve as many questions as you can from VSEPR Theory, because trust me, it is going to be very, very easy for you to now solve questions based on VSEPR Theory, right? Now there's one particular exception which I do not think will be asked at a bachelor's level. At a master's level it can be asked, but you never know that Indian IITs can actually ask you tough questions as well at a bachelor's level. So I would recommend that you go and watch my video for sure. That video is very important because it contains certain exceptions. So you can just click the link over here. I'll attach the link somewhere over here on the top left corner, your top right corner, my top left. Okay, and just go and watch that video, because I do not want you to lose any marks based on VSEPR Theory, at least, right? Anyway, all the best.